Hello and welcome to my third proof. My name is Kevin Kahn, senior at Cal State East Bay, and this is the proof of Demoivre's theorem. I have no idea how to say his name correctly. I might say it wrong the whole time, but I'm going to say it consistently wrong the whole time. So here we go. Our overview is we're going to kind of show what Demoivre's theorem is, a couple uses of it. Then we have to prove Euler's theorem. It's actually Euler's formula. We will prove that as it is very useful in proving Demoivre's theorem. Then we will actually prove Demoivre's theorem, and then we will go through one example. All right, so let's get her started here. If you've never seen Demoivre's theorem, you have company in me about 2 weeks ago. I had never heard of this theorem before being assigned this proof. It involves complex numbers and raising them to powers. And it's, man, pretty crazy, but pretty cool. It connects complex numbers and trigonometry. Also, these ends have to be positive integers. I just made them the natural numbers, and by the axiom of convenience, I am not including 0 in the natural numbers. People have opinions on that, but I'm not here to debate that. Yeah. We also, so we connect complex numbers and trig. We can raise complex numbers to powers, and then we can also find roots of complex numbers. I'm not gonna do any examples of finding complex number roots. We are just gonna go over raising complex numbers to powers. And as you can see, this here is the formula. You start with a cosine x plus a I sine x with an r out there, and you're raising everything to this positive integer n. And then as you can see, the n slides in here and raises the r to the positive integer power, and it also just slides in here nice and neat with those x's. Usually, I mean, well, I guess not usually, those are going to be angles. So this can also be shown as theta instead of x, but I wrote x and I tried to be consistent in writing x. So here we go. Euler's formula, which, man, it makes Demoivre's proof a lot easier. Here we go. This is the left-hand side of Demoivre's formula minus that integer power, but we'll deal with that later. And Euler said that is equal to r times e to the I theta. I realize, sorry, that I switched these thetas and x's, but I think from here on out, I'm pretty consistent. So we're going to start the proof here. It's relatively informal, although it has all the necessary pieces. I don't have a set of givens, but this does require the Taylor series. And if you don't remember the Taylor series, or not great with the Taylor series, or not familiar with the Taylor series, it's not my strongest suit, so I definitely had to refresh myself on the Taylor series. It is right here. It is a sum, and this Fn to a chosen x naught, this is the nth derivative at this given x naught. This and this x naught are the same. And then you do x minus x naught to the n over n factorial, and you keep going for a bunch of n's, and then you sum them up. So we are centered at 0, 0. So our x naught will be 0. And we're going to look at cosine first. So I just went ahead and calculated here the first 5, well, I guess the first 4 derivatives, including just cosine of 0. And color coded them a little bit here. So cosine of 0 is 1. The first derivative of cosine, negative sine. So negative sine of 0 is 0. And if you're unfamiliar, these just keep flip-flopping back and forth, and there's a negative in there. I think we all... My audience for this video is senior math majors in college, so I think we all should know that at this point. Here we go, color coded. This goes here, 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 here. As you see, we have some zero terms. So these zeros are going to wipe out that whole term. The first term is 1 times x minus 0 over 0 factorial. This will just become a nothing. X to the 1, x to the 0 is 1, 0 factorial is 1. So this is 1 times 1 over 1, which is 1. This term comes from here. We get a minus because of this minus 1 out front. This just becomes an x squared. And our bottom part doesn't really change. That's just the 2 factorial. And so our pattern repeats. We pick up all the even powers of x, and they alternate signs, starting with a positive, negative, positive, negative, positive, negative, positive, negative, and so on. We could write this out to however far we want. The pattern stays the same. This is the expansion of a Taylor series for cosine. Now we're going to look at sine. I went ahead and, and the reason we know this is this pattern repeats. Right here, you're already at the top, and then you go back into the cycle. That's going to be the same for sine here. I went ahead and calculated the first 4 derivatives, including just, I went ahead and calculated out the first 4 derivatives of sine, as well as sine just as it is. Again, we're centered at 0, so our x naught is 0. Sine of 0 is 0. Then our derivative goes to cosine. Cosine of 1 is 1. This is repetitive from the last one. And so cosine of 0 is 1, sine of 0 is 0, and then we get here and we're back at the top, so our pattern repeats. Again, I tried to color coordinate it. This goes here, this 0 goes here, this 0 goes here, this -1 comes here. So this term will be negative. This gets wiped out. This gets wiped out. This gets wiped out. And you can see here, this x over 1 factorial. 1 factorial is just 1. So this is just an x term out here. And we're picking up all the odd powers of the expansion. So we're just getting all the odd stuff. And again, this is a plus, this is a minus, this is a plus, minus, plus, minus, and that repeats just with the odd powers of the expansion. So we have on the left side of Euler's formula, we have cosine and sine. We've expanded those. We see what that looks like. And now we got to look at this E I theta. First, we're going to look at just the e to the x expansion of a Taylor series, and that's 1 plus x squared over 2 factorial plus x to the cubed over 3 factorial. It picks up all of the pieces, and there's no changing of signs. But that's e to the x, and we need e to the ix, or I theta, I variable. Our formula has an I, so we're going to add this I in anywhere we see an x. So now instead of regular x, that's ix. That's ix squared over 2 factorial. That's ix cubed over 3 factorial. That's ix to the 4th. over 4 factorial, and so on. But we still don't have any changes of signs. That's okay, because if you recall, I squared is -1. So I to the first is just I squared is -1. I cubed is -I, because that can be broken down into I to the first times I squared, and that's I times -1, and that gives us our -I. I to the fourth can be broken down into I squared times I squared. -1 times -1 is +1. And our pattern repeats from here, similar to the way I was breaking it down. I to the fifth is just I to the first times I to the fourth. So that's 1 times I, and that's just I. I to the sixth is I squared times I to the fourth, and that's -1 times 1, and that's -1. So on. I to the seventh is I to the fourth times I to the third. That's -I times 1, -I. I to the eighth. We can go on. The pattern repeats from I to I to the fourth. A lot of repeating patterns in this thing. It's kind of nice. So now we put these I pieces in. This becomes a negative because we have I squared here. So that term is now negative. This also becomes negative, but the I stays because it's a -I. So we have minus I x cubed to the third. X cubed over 3 factorial. I mean, this I to the fourth keeps this term positive. This I to the fifth also keeps this term positive, but it keeps an I out there because I to the fifth is +I. This makes this term negative. This makes this term negative with an I. So that's where we get this. So we have this kind of weird pattern where it's the sign doesn't change every time, but it changes when we go kind of up 2 powers. So there's 2 powers here. There's no x, and there's an x to the 0 here. I guess those may be kind of outliers. But then we have minus x squared over 2 factorial minus I x cubed over 3 factorial plus x to the fourth over 4 factorial plus I x to the fifth over 5 factorial minus, minus, plus, plus. And if you kept going on, it'd be minus, minus, plus, plus. So then we're going to take this giant expansion and group the like terms. So everything that has that has no I is going to be over here on the left. Everything that has an I is going to be here on the right. And we're also going to factor out the I. So no I over here, no I over here, no I over here. I term over here, I term over here, I term over here, I term over here, I term comes out, comes out, comes out. So we have that I out in front. And you maybe just noticed, or not just noticed, maybe you noticed that this piece here is the Taylor expansion for cosine of x. We're picking up all the, this is cosine x. We're picking up all the even terms and we're alternating sign. Even terms, alternating sign. And this is sine x. We're picking up all the odd terms, odd powered terms, even powered terms, and we're alternating sign. And we have this I out front. And remember, this is equal, this whole piece is equal to EIX. So we can say that EIX is equal to cosine x plus I sine x. And if we just multiply both sides by R, then we have just proven Euler's formula, which says R cosine x or theta plus I sine theta is equal to R times e to the I theta. Okay, are you ready to prove Demoivre's theorem? It is incredibly long and complex. There are two ways to do it. We meaning my co-prover group, all chose to do it the same way. You can do it by induction, or you can do it the way we're going to show you right here. Get ready. It's a doozy. So remember, this is what we are proving here, that r times this cosine plus I sine theta raised to the n is the same as Rn times cosine n. I feel like now I'm mixing up my x's and thetas. Man, I tried to keep this straight, but it's hard. But here, we just put the n in. It comes from up here into here for both of them. And then the n or the r out front is also raised to the n power. So we can say r cosine x plus I sine x is equal to r e to the ix. Thank you, Euler. That is a huge, I mean, Demoivre's theorem proof gets so much longer if you don't prove Euler's theorem elsewhere. If you prove it in here, this proof is really long. But I was joking. It's not a doozy. It's actually really short. This is it. The hard part is proving Euler's formula. So if we raise this bit to n, then you, using exponent rules, you distribute this in n in, and it also comes out to the r. So we can say that this bit is equal to this piece. All we did to both of these was put an n up there. So this piece is this raised to the n, and we just showed what that is. And all we did was throw an x in here, or an n in here, and we know what this is. According to Euler, this right here is this. And the only difference is an INX, and we just throw that bad boy right next to the x inside the sine and the cosine. What we have here is a string of inequalities. So we're just going to pick out this inequality, or this portion, sorry, not inequalities, equalities. So they're all equal. So we're just taking this bit from the equality, setting it equal to this bit from the equality. And that's it. That's the proof right there. That is the proof of Demoivre's theorem. Now you might be thinking, despite what I showed up here, that this theorem connects complex numbers and trigonometry. Hint, hint, hint. I think that's question 1 on our homework. You can also raise complex numbers to powers and find roots. I'd be thinking, how the heck am I supposed to do that? Well, I'll show you. Here we have an example. So now I want you to find 2 plus 2i to the 6th. But wait, that's like a rectangular Cartesian deal, and we've been dealing with polar. Where's the r? Well, all this is an x plus I y, or yi. It's the same. So we can go out and we have to change from this Cartesian or rectangular coordinate to a polar coordinate. And what we need in polar is a radius and an angle theta. So we can find that. This point here is 2, 2, our x and our y. And if you recall from calculus, I think Calc 3, I know we touch on it a little bit. R squared is equal to x squared plus y squared. Take the square root of both sides. R is equal to the square root of x squared plus y squared. We also, there's a way to go back and forth by looking at the cosine and the sine of each of these. So the cosine is the adjacent over the hypotenuse, which we have here. Sine is the opposite over the hypotenuse. If we just multiply both sides, excuse me. If we just multiply both of these bits by r, we get r cosine theta equals x. And remember, this here is just an x plus an iy. So x plus iy, we can replace the x and the y with these bits here. And we get x plus iy is the same as r cosine theta plus I times r sine theta. We can pull that r out, and then we just get r times cosine theta plus I sine theta. And that looks like something that we can deal with. There's also this other way of finding r. So I am going to use that and find r, and then find our theta, and then we're good. We can implement Demoivre's theorem and find out what 2 plus 2i to the 6th is without having to multiply 2 times 2i, 2 plus 2i 6 times. So x and y components are 2. So 2 squared plus 2 squared is 8. We pull out the 4, and that becomes a 2 outside of the square root. So r is 2 root 2. Just use the inverse tangent function, and I'm going to keep it in radians rather than degrees, and we get pi over 4 is our theta. So now we have x plus I y equals 2 root 2 times cosine of pi over 4 plus I sine pi over 4. And we want to raise this whole bit to the 6th. So I took the liberty of just applying Demoivre's theorem. That's all we're doing to go from this right here to this. That's the beauty of Demoivre's. It makes it really, really simple. This is like, I don't actually know, this is sort of conjecture. It's like a counterpart, like a complex counterpart to the binomial theorem. Kind of. It's probably apples to oranges. I don't think that's comparing apples to apples. But we take r, raise it to the 6th, and then we multiply our angle theta by the same exponent. So 6 times pi over 4 plus 1 times sine of 6 times pi over 4. This cancels out. We're left with a 3 pi over 2 for our angle. So that is the same as we have cosine of 3 pi over 2 plus I sine 3 pi over 2. 3 pi over 2 is the same as 270, and that has no x value. So this term is going to be wiped out. We're only going to be left with the deal here, and that's a -1. I'm going to make that blue. That's a -1. And then now all we need to do is calculate this 2 times square root of 2 to the 6th. So that's the same as 2 to the 6th times square root 2 6 times, which you can look at it as, I'm going to erase this cosine piece since we know it doesn't come into the equation here. that by itself. Another way to look at that is square root 2 times, that'd be square root 2 6 times, or you can just write it 3 times and have it squared. So that cancels out, blah, blah, blah. The root and the power, so that's really 2 to the 9th times -1i. Almost forgot the I. And that's what we get our 512, -512i from. So there you go. That's Demoivre's theorem with a little example changing from rectangular to polar. And if you want to go from polar back to rectangular, you will use this stuff here. And there's one with tangent that's easy to figure out. Anyway, all right, thanks for joining. And if you're watching over break, have a nice break. If not, welcome back.